Bonding in carbon. Properties of some of the carbon compounds. Let us have a look at the melting point and boiling points of some of the carbon compounds. Carbon compound methane, that is CH4, has a melting point 90 Kelvin, boiling point 111 Kelvin, and a physical state, gas. Ethanol, that is C2H5OH, has a melting point of 156 Kelvin, boiling point 351 Kelvin, and is in liquid state. Chloroform, CHCl3, has a melting point of 209 Kelvin, boiling point 334 Kelvin, and is in liquid state. Acetic acid, that is CH3COOH, has melting point 290 Kelvin, boiling point 391 Kelvin, and is in liquid state. Most carbon compounds are poor conductors of electricity. From the data on the boiling and melting points, we can conclude that the forces of attraction between these molecules are not very strong. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds does not give rise to any ions. The element carbon, C, is a non-metal with atomic number Z equal to 6. Its mass number is 12. Its atomic mass is taken as 12U. The electronic configuration is 2, 4, which means it has 2 electrons in the K shell and 4 electrons in the L shell. Since it has 4 electrons in outermost shell, that is L shell, its valency is expected to be equal to 4. We know that the reactivity of elements is explained as their tendency to attain a completely filled outer shell, that is, attain the noble gas configuration. Elements forming ionic compounds achieve this by either gaining or losing electrons from the outermost shell. In the case of carbon, it has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain the noble gas configuration. If it were to gain or lose electrons, 1. It could gain 4 electrons to form C4 negative anion, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is, 4 extra electrons. 2. It could lose 4 electrons to form C4 positive cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus, holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon, or with atoms of other elements. Not just carbon, but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outer shells of both the atoms and lead to both atoms attaining the noble gas configuration. Let us now take a look at methane, which is the simplest compound formed by carbon. Methane is widely used as a fuel and is a major component of biogas and compressed natural gas, that is CNG. Methane has a formula CH4. Hydrogen, as you are already aware, has a valency of 1. Carbon is tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen as shown on the screen. Such bonds, which are formed by the sharing of pairs of electrons between the 2 atoms, are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are small. This gives rise to the low melting and boiling points of these compounds. Since the electrons are shared between atoms and no charged particles are formed, such covalent compounds are generally poor conductors of electricity. Covalent bonding in some other simple molecules. Let us look at some simple molecules formed by the sharing of valence electrons. The simplest molecule formed in this manner is that of hydrogen. The atomic number of hydrogen is 1. It has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So, 2 hydrogen atoms share their electrons with each other to form a hydrogen molecule H2. This allows each hydrogen atom to attain the electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. We can depict this using dots or crosses to represent valence electrons. The shared pair of electrons is said to constitute a single bond between the 2 hydrogen atoms. A single bond is also represented by a line between the 2 atoms. The atomic number of chlorine is 17. Its electronic configuration is 2, 8, 7 and its valency is 7. When 2 atoms of chlorine come together, both have a tendency to gain electrons. So atoms share their electrons so as to attain noble gas configuration. Chlorine forms a diatomic molecule, Cl2. In the case of oxygen, we see the formation of a double bond between 2 oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8 and it requires 2 more electrons to complete its octet. So, each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure as depicted on screen. The 2 electrons contributed by each oxygen atom give rise to 2 shared pairs of electrons. This is said to constitute a double bond between the 2 atoms. Water exists as a molecule which has 2 hydrogen atoms and 1 oxygen atom. The formula of 1 molecule of water is given as H2O. Have a look at how sharing of electron pairs takes place. Let us now learn what happens in case of diatomic molecule of nitrogen. Nitrogen has the atomic number 7. Its electronic configuration is 2,5. In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This forms a triple bond between the 2 atoms. The electron dot structure of nitrogen, N2, and its triple bond can be depicted as shown on screen. Properties of covalent compounds. Physical nature. Covalent compounds are typically gases, liquids, or low-melting solids. Few common covalent compounds which exist as liquids at room temperature are H2O, CCl4, CHCl3, Br2, etc. The melting and boiling points of covalent compounds are generally very low. They exist as gases, volatile liquids, or low-melting solids. Covalent bonds hold atoms very strongly. Example, Cl single bond Cl, that is, Cl2 molecule. Only requirement of melting a covalent compound is to separate molecules from each other. The forces which hold the covalent molecules together are weak van der Waals forces of attraction. The intermolecular forces of attraction are very weak, and hence covalent compounds normally exist as gases, liquids, or low-melting solids. Van der Waals forces of attraction in bromine are greater than in chlorine. That is why bromine is a liquid and chlorine is a gas at room temperature. Solubility. Covalent compounds are normally insoluble in water but are soluble in non-polar organic solvents. A few covalent compounds like glucose, sugar and urea are soluble in water. These are exceptions. Covalent compounds dissolve in covalent solvents. Electrical conductivity. Conduction of electricity is possible by migration of ions or by migration of electrons. Covalent compounds do not conduct electricity as they do not contain free electrons. They are poor conductors of electricity. Allotropes of carbon. Some elements can exist in different physical forms. Allotropy may be defined as the property of an element as a result of which it exists in more than one form that are physically different and chemically similar. Some elements which can exist in different physical forms or allotropes are diamond, graphite, fullerene. The 3 different forms of carbon have different physical characteristics. Diamond is hard, shiny and bad conductor of electricity. Graphite is black, soft and good conductor of electricity. Fullerene is an allotrope of carbon which is recently discovered. It has a unique structure. All these allotropes are made up of carbon. The difference between allotropes of carbon is due to the manner in which the carbon atoms are bonded to one another. Diamond. Diamond is the hardest crystalline form of carbon and is present in different parts of the world as a constituent of hard rocks. Diamonds are mainly found in North America, South America, Africa, and Australia. In Asia, it is found in India in Panna district of Madhya Pradesh and in Vajrakarur in Andhra Pradesh. In nature, diamond exists as transparent octahedral crystals with curved surfaces. Their beauty is revealed when they are properly cut and polished. Let us now discuss the structure of diamond. In diamond, each carbon atom is bonded to 4 other carbon atoms by covalent bonds. This forms a 3-dimensional network resulting in a tetrahedral structure. Each carbon-carbon bond length is 154 picometer. As the carbon atoms in diamond are very closely packed in space, it is very hard with a density of 3.5 grams per cubic centimeter and has a very high melting point of 4000 Kelvin or even more. Because of its high refractive index, that is 2.42, it produces maximum total internal reflection responsible for its bluish-green color. Since all 4 electrons of carbon are involved in bond formation, in the absence of free electrons, diamond is a bad conductor of electricity. It is also a poor conductor of heat. Strong heating of diamond in presence of air results in formation of carbon dioxide gas, which shows that diamond is pure carbon. Due to its hardness, diamond is used for cutting glass. Glass cutters are made out of diamond as it is the hardest natural substance. Largest diamond ever found is 3106 carat and is called Cullinan. Kohinoor, also called Mountain of Light, is of 108.93 carats. Diamond Hope is of 45.52 carats. Graphite is another crystalline form of carbon which occurs in the free state. The word graphite is derived from the Greek word grapho, meaning right. It is greyish-black, opaque and slippery substance. It is a good conductor of electricity. If graphite is heated in presence of air, it forms carbon dioxide gas. Graphite is found in India in Jammu Kashmir, Rajasthan, Uttar Pradesh, Bihar, Orissa, Andhra Pradesh and Tamil Nadu. Structure of graphite. Each carbon atom is linked to 3 other carbon atoms by covalent bonds, resulting in hexagonal rings which are arranged in layers. The carbon-carbon bond length is 142 picometer. These layers are held together by weak van der Waals forces of attraction, and the distance between the layers is 335 picometer. Graphite is relatively soft and greasy because its structure is not compact like diamond. Its color varies from steel grey to black depending upon the origin and has a metallic luster. But unlike diamond, it is opaque. Its density varies from 2.0 to 2.25 gram per cubic centimeter. Since one electron of each carbon atom is free to move about, therefore, graphite is a good conductor of electricity. It is a good conductor of heat as well. Graphite is used to make electrodes for cells in which the process of electrolysis is carried out. Mixed with wax and clay, graphite is used for making cores of lead pencils as it can mark paper black. It is often called black lead or plumbago. Melting point of graphite is 3730 degrees centigrade. So graphite crucibles can withstand very high temperatures and can be used for melting substances with high melting points. Graphite is used in preparation of diamond by high pressure, high temperature synthesis. At temperature of 3700 degrees centigrade, graphite converts into diamond. Fullerene. Fullerenes represent recently prepared allotropic form of carbon. They have been found to exist in the interstellar dust as well as in geological formations on Earth. They are large, gauge-like spherical molecules with formulae C32, C50, C60, C70, C76, etc. The most commonly known fullerene is C60, which is named as Buckminster fullerene after the designer of the geodesic dome by an American architect, Buckminster. Structure of C60 molecule. C60 molecule has a symmetrical structure. It is a fused ring of aromatic system containing 20 hexagons and 12 pentagons of C atoms. The structure bends around and closes to form a soccer ball shaped molecule. C60 is therefore called buckyball also. The diameter of ball cage is about 70 picometer. It is about 6 to 10 times as large as hydrogen atom is. The ball cages are highly stable and do not break up till 1375 Kelvin. It is a highly symmetrical structure in which all the carbon atoms occupy identical position. Appearance and applications. C60 fullerene looks different from diamond and graphite. It's a yellow powdery substance which turns pink on dissolution in solvents like toluene. Fullerenes show unusual characteristics and applications like they are wonderful lubricants because the balls can roll between the surfaces. Fullerenes also act as superconducting materials even at high temperatures of the order of 10 to 40 Kelvin. Let us have a look at an animation to understand this in a better way. As you see in the animation, Buckminster fullerene are molecules with 60 carbon atoms. It looks like a hollow soccer ball molecule. Notice that it is formed of hexagons and pentagons. There are 20 hexagons and 12 pentagons. They were first discovered in 1985, where it was found that atoms are arranged in hexagonal and polygonal forms. Let us have a look at few other kinds of fullerenes. C70 fullerene is such an example. Notice the 10 green atoms in the middle. Another example is C540 fullerene, which exists as icosahedron. Notice the 10 faces in 10 different colors. Let me tell you one more example of a fullerene. It is called as a carbon nanotube. It exists in the form of a tube. Its name is derived from the long hollow structure with the walls formed by one atom thick sheet of carbon. Sheet rolled at specific and discrete angles decides the properties of nanotube.